Hello and welcome to today's webinar. This is a 3D Printing 201 webinar, and we are going to be focusing on an application just like we have been doing with our 3D Printing 201 series. And today's application is going to be injection molding. So we're going to spend about 20 to 30 minutes talking about how we are seeing people use 3D printing to supplement modern day injection molding processes. We're going to be covering some FDM and some PolyJet, but we're going to be focusing on the PolyJet applications because they're really a best fit for the injection molding application. If you're new to 3D printing, or if you're new to the Stratasys line, I encourage you to watch this, and then once we're done here, hop on GoEngineer's YouTube page and check out our 3D Printing 101 webinar, which covers FDM and PolyJet technologies, beginning with the most basic applications, and really discusses what they are and how they're used. And then move over to the 3D Printing 201 webinar series, which talks more about applications. So injection molding, we're going to begin with a little bit of an overview as to what injection molding is so that everybody watching today is on the same page. If at any point you have a question about what we're talking about or a question that you'd like me to answer, go ahead and type that into the GoToMeeting questions box or the chat box. I will be addressing the questions at the end of the webinar here today, but that will absolutely add to the webinar, so go ahead and ask those in the question box. So as for an overview of injection molding is a process that is used to create parts out of thermoplastic materials. Thermoplastic materials are plastics that are, when heated up and then cooled, they harden. This is opposite of an elastomer. Typically, this process involves a machine that looks like that very simplified image that we have there at the bottom of the screen. If you see that image there is numbered, and I'm just going to walk through those and kind of give you guys an idea of what's involved in this injection molding process. Number one is it's an Archimedes screw, essentially. That's a screw that's going to move the plastics down this tunnel. Number two is a funnel, and this is where the plastic materials or the plastic resins are loaded into the machine. So you have plastic pellets or resins dumped into the screw chamber. In that screw chamber, there is obviously a screw that's moving the pellets from left to right in this image, and there's also would be some heating blankets. So as the materials are pushed down this screw, they're melted and the pressure is increased. So by the time it gets to the valve, which is number 3 there, we have molten high pressure plastic. So number 4 is a solid mold tool, and we would call this the cavity tool, and this is stationary. Between 4 and 6, those two parts together, that would be called our mold tooling. And these two parts, when they're brought together, they form a cavity. And within that cavity is what we will eventually inject this hot molten plastic, and the plastic will fill this cavity and then create our part, which is number 5 in this scenario here. So that's a basic overview without giving you in too many details or showing a video of how that works. Injection molding is a very high volume manufacturing process where, if you think about your Legos, those are injection molded parts, and how many kids had hundreds and hundreds and even thousands of Legos? Those would all be created with injection molding, because injection molding is very fast, it's very quick, it offers good repeatability, which is important in the case of Legos, right? Because all the parts need to be able to snap together repeatably. But it does come at a high tooling cost. Okay, so parts number 4 and 6 in this little image here, these would be very expensive. So that brings us over to the next aspect of injection molding, and that's the tooling. All right, so we have some typical injection mold tools here. We have a core and a cavity on each tool. Along with the core and cavity, which really creates the geometry of the tool, which forms that empty void of space, We have some other portions. We have gates and we have runners. These are pathways for the plastics to move between the cores, between the cavities, and between the parts. We also have some additional parts to allow us to move these tools together and apart repeatably. We also have say cams and sliders that would allow us to come in from the sides or from the top, so we can get undercuts, so we can get very complex geometry inside our mold tooling. And then we'd also have an ejection system in here, which, going back to this last image, once the hot plastic is injected into the cavity, there is a certain amount of time that's waited to allow the heat to dissipate into the mold tooling, and then number 6 would be pulled away and the part would come with that, and then some ejection pins would actually push that out. We call that the ejection system. And typically this mold tooling would be created out of steel or aluminum. Okay, so we talked about these parts having to withstand high pressures, high temperatures, be able to pump out parts very quickly. That's where the heat dissipation comes into play, and be able to hold up to create thousands upon thousands upon thousands of parts. So there's a durability issue as well. So that's why these typically are made of steel or aluminum. So where is injection molding used? Well, looking in front of me right now at my desk, I'm working on a laptop where the entire casing and all of the buttons in my keyboard are injection molded. The mouse in my hand is injection molded. The housing around my computer monitor is. I probably have more injection molded parts than anything else in my office here. My phone, my hard drive. Lots of products are injection molding. A lot of housings, a lot of casings. If you think about your hair dryers, your sunglasses, but there's also a lot of automotive and aerospace applications as well, especially if you're using, everybody gives a hard time to the domestic car manufacturers because the interiors are all plastic. Well, they use injection molding machines to create those. So it's typically high volume parts. So where does 3D printing come into this scenario, right? Everything that I've said so far is kind of lays outside the realm of 3D printing. So if you're watching the 201 webinar here, you're probably a little bit familiar with 3D printing. You know that additive manufacturing or 3D printing is more geared towards low production, short run, low volume parts where you might be making 1 to 5 to 10 to 100 parts. Okay, so how does this come into play? Well, we can use 3D printing alongside injection molding in 2 ways. The first way is part prototyping. Okay, so this would be taking the final part that you need. Say it's one of the parts here in the images here. We've got tarp clips and we have what looks to be a GPS unit. Those parts, we know the final part was going to be injection molded. Okay, but we talked about injection mold tooling is very expensive, and you usually only want to create that tooling one time. And how often do we get designs right on the first time? Hardly ever, right? So I know for a fact these tarp clips on the left, they went through several design iterations before the final design was decided upon. So there's a few things, even though these are a simple part, there's a few key aspects of these tarp clips that are required for them to operate correctly. They have to be able to hold a certain amount of force. So they have to be able to clamp onto the tarp with adequate amount of force. So we not only have to be able to slide those up and lock them into place and pull on the tarp clip and not have it pull off the tarp, but we also have to be able to release those, and there's a little button to release those. So the inventor of these tarp clips actually went through several design iterations, and he 3D printed these design iterations, and there might be, these tarp clips might show up in a few other videos because they're one of the success stories that we've had with alongside Stratasys. So even though these were injection molded, he wouldn't want to create the injection mold tooling so early on that you'd have to go back and change the tooling several times in order, because you have design changes. It's going to cost a lot of money. We were talking with some guys from Polaris and Polaris snowmobiles, and they have some injection molded parts on their snowmobiles, and they came to Stratasys and they said, hey, for this particular part, it was a luggage carrier rack, for this particular part, the changes that we make to the mold typically run us $60,000 every change that we make. So they started prototyping their luggage racks before they started making changes to their mold. And even though they spent $1,000 in 3D printing, they were able to forego $60,000 worth of mold changes. So this is one instance where 3D printing comes into play alongside injection molding, is actually printing the part. On the other image there, that GPS housing, and this is kind of a unique case because we have an overmold situation, which is very difficult to prototype in a conventional sense. When I say overmold, I mean we have some rubber-like material that's been molded over a hard material. So in that image, we have a very light gray plastic. That's an opaque, rigid plastic. But then also we have that black material, and that's a rubber-like material that's been printed directly off a Connex machine using our PolyJet technology. And this way they're able to simulate the overmold situation. Now this part would undergo an injection mold process called a two-shot process, where you have a single shot of that hard opaque plastic, and then you have a single shot of a rubber-like material. Okay, so in this situation, we're prototyping the parts, and because we're printing the parts directly, we're limited to the materials that we can print in, right? So in FDM, like the parts on the left, those tarp clips, we're limited to ABS plastic or polycarbonate or PCABS or some of the other high performance materials, but we can't print those in, say, polypropylene, right, or polyethylene. And same with the Connex machine. And on the PolyJet side and that GPS, we can't actually print in rubber. We print in a simulated rubber. Okay, so that brings us to the next scenario here, where we actually need parts that are in the final material, the true to spec material. So we can't print them directly. What that leaves us with is creating some injection mold tooling and going through the molding process with the true materials. And as I mentioned, that's a long, lengthy, expensive process. So what we're doing now is we're actually printing the injection mold tooling. So this is a PolyJet only application, and really we're going to be using the digital ABS or ABS2 materials that are available on the Connex machine. We have seen people use the Vero materials that are available on the Objet Pro machines, but they're not quite as durable as this green ABS, digital ABS material. But here what we're doing is we're printing the core, we're printing the cavity, we're mating them up together. We're not touching, there's zero hand finishing on these parts. The only thing we might be doing is adding the inserts that we talked about earlier, the gate system, the sliders, the injection pins. We would be adding those to the digital prints, and these would be inserts into the mold. So you can see over on the right hand side we have a print that has some bushings inserted. We have on the core, which is on the bottom of the image, we have lots of holes in the part. Those are for the injection pins. That's for the ejection system. So these are actually going to be printed. They're going to be loaded up into the machine, and we're going to be injection molding into these. So going back to the traditional process, we talked about this process being lengthy and expensive, and it's really something that you can't avoid. Okay, so typically the tooling is machined. It's machined out of steel, or in the case of soft tooling, it'd be machined out of aluminum. There's a lot of steps in the process, and there's a lot of hands in the process of machining. You have design of the mold, but then you also have a CAM programmer who's going to be programming the CNC machines to cut those. And for mold type situations, the programming of those molds can take days, it can take weeks. If we're lucky, we're going to be milling it. All right, so we load it up to the mill machine, and if we're really lucky, it's only going to be a 3-axis process. But it's not uncommon to have 4- and 5-axis processes on these mold tools. If we have very strict requirements for the surface finish, if they're physically large parts, if there's some unique geometry, we're going to find a 5-axis machining center, and we're going to machine it in 5-axis. If we're a little bit unlucky, there's going to be some very small features or some very tight or sharp internal corners, and we're going to have to go and get these EDM, which is even more expensive because there's even more tooling that has to be created for your sinker EDM process. So that's a very time-consuming process that eventually you might have to do that, right? So I'm not saying that we're going to replace these all together. In some cases we might, but in reality, we're going to still have to do this eventually. But this is something that you don't want to have to do more than once. And the reality is a lot of people are doing this more than once because of design changes, because of issues with the mold, issues with suppliers, and things are going wrong. There ends up being changes to the mold, and we try to avoid those. All right, so we really want to vet out the mold before the investment's made in the machine mold. There's also the idea of cast tooling, like a urethane cast tooling. Again, this is something that is time consuming. It's cheaper than a machine tooling, but it's not as durable. So there's a trade-off there, just like we have trade-offs with all of these. So some of the things we have to consider is that it's very labor intensive. You know, again, it's not uncommon for mold tooling to take weeks and months to come back from a vendor. And the costs, if they're in the thousands, that's a very cheap mold. If it's in the tens of thousands, I would say that's an average mold. And if it's in the hundreds of thousands, that's an expensive but not uncommon mold. So the PolyJet process is going to look a little bit different. Instead of machining an aluminum mold or casting a soft tooling, we're going to be creating these mold or tooling inserts. So if you see the image there, the green portion of the mold tooling is the printed portion. Behind that, we have an actual mold tool with some gold inserts. So in the previous image with the scissors handles are cut directly into the mold base. In this situation here, where we've got the printed inserts, the outside or the housing of the mold tool is still machined, but that's a very easy, very efficient way to create that part because it's very prismatic. The most expensive, the most time-consuming, and the most complex portion of the mold is printed, and then it's inserted into the mold tooling. So in this situation, there's little to no CAM programming, and there's no months and months of lead time. Something like this will be printed typically in a single day. Okay. So the advantages here is that it's much quicker. It's much less expensive, especially when you start to consider design iterations. So going back to those tarp clips, I know for a fact that those went through at least 2 to 3 design iterations. And if that step didn't happen, and if you went straight to mold tooling, now you're talking about an initial investment on the mold tooling, but also investment into changes. And that's money that's just wasted. It really is. So the advantages here is that it's cost effective and it's efficient. Again, going from months down to a single day to print these. It also helps people offload work from other backlog operations. You know, these tools, the injection mold machines, are run day in, day out. They're very busy machines, and same with the milling machines and the other manufacturing, the machining centers and whatnot. They're run constantly. So any sort of help that we can give to those machines, anything that we can move away from those machines, helps the process. So the next couple slides are actually going to give some hard numbers about these printers because we talk a lot about this injection molding process, and if you go on Google and you search injection mold 3D printing, you can find actually a lot of reporting on people doing this, but it's very difficult to find specific numbers, and that's really what it comes down to. If you're interested in this application, if you if you have in-house injection molding capabilities and you're familiar with the processes, then you're going to have very specific questions about what you can mold and what you can't inside a 3D printed part. And if you don't do things in-house, if you send it out to, if you have injection molded parts and you send it out to a vendor, these are the questions that they're going to come back and ask as well. So let's talk about when this makes sense and when it doesn't. So we're going to be dealing with thermoplastics, obviously. There's a few different attributes with those thermoplastics that make each material suitable for a 3D printed injection mold tooling. One of those is the molding temperature. What temperature is that plastic going to be when it's injected into the tooling? So for our digital ABS 3D printed tools, we like to see that temperature less than 300 C or about 570 F. All right. We want plastics that have good flowability. Okay. So we're going to be seeing a chart here in the next slide here that groups up some of these plastics in terms of flowability and other attributes. Low quantity runs. So we're not going to be creating Legos out of these printed parts. We're going to be creating prototypes or end-use parts that are in the 5 to 100 quantity size. And I say 5 to 100 shots, not parts, because some of these tools create one part, but some of them create several parts. So it's 5 to 100 shots. Let's say mid-size parts, less than 10 cubic inches volume of material. Mid-size press, 50 to 80 ton press would be about the limit that you'd want to run these on. And really the best fit situation is where you need a part that's created from the true spec material, and you need it prior to developing the full final production mold tooling. All right, so these are some of the situations. If you fall within these situations, then this is something you should be looking at. So the question comes up, how durable are these prints? What would cause them to be less durable? And what sort of situations would I want to avoid? So the material that we're actually injecting into the part is obviously one aspect or one unknown that can cause some tool life issues. So different plastics are going to be more compatible or less strenuous on our printed tooling. All right. Also the part geometry. If you have very high draw or very thin parts, that's going to be harder on the tooling than if you have thick walled parts with a low draw. So the best fit would be a material that flows well, meaning it requires less pressure, a low melting temperature, less than 570 F, and really opaque materials. So clears and transparent materials, clear and transparent thermoplastics, we haven't really seen a lot of success with those yet. So the specific materials that we're talking about are kind of displayed in this graph here. So what we're looking at is 4 different groups of materials, A, B, C, D. In this 3D graph, we have A, B, C, D down along the X, and we have a quantity of shots in the Y. In the Z, we have different groups of mold tooling based on the material of the tooling, okay? So at the front of the list, we have the PolyJet, our printed tooling. And at the back of the list, we have their steel and aluminum, your conventional tooling, okay? So what you're seeing here is that the steel and aluminum tooling is going to be the most robust. It's going to be the most durable, no matter what material you're using, all right? And that makes sense, right? In the front of the list, we have the PolyJet, our printed tooling, and we'll see for Group A, we're going to be at or above about 100 shots on our tooling. Group B a little bit less, Group C a little bit less, and Group D pretty much uncompatible with our printed tooling. We also have some other options for the tooling in there. We have the cast resin tooling that we talked a little bit about earlier. You can see it's a little bit more robust than the printed tooling, but it's also labor intensive, just like the other tooling options. We also, in the green, we have the DMLS option as well. So DMLS, if you're not familiar with it, stands for Direct Metal Laser Sintering. It's 3D printed metals, okay? So you can see in Group A, it's very durable, but it also goes down as you get into some of the more, the less flowing materials and a little bit more strenuous materials to inject. So what I take out of this is that outside of Group D, we can actually print tooling for injection molded parts that are injection molded out of these materials. We have a lot of common materials in there. We have polyethylene, got polystyrene and ABS and polypropylene. Group A is going to be some of the most common materials that our parts are around us. Group B contains some polyamides and acetyl, which again are still very popular. And then within Group B and Group C, we even have some glass-filled options and we have some polycarbonate options as well. So there's a wide range of materials that we can actually use our printed tooling on. Now, our printed tooling is not going to last as long as some of the other tooling options, but it's going to come at a very steep discount in terms of both time and cost. So at the end of this webinar, I'm going to show a success story, and that will hopefully get across the point about where the printed tooling fits into play here. It's not going to replace steel and aluminum tooling. It's not going to replace even cast resin tooling entirely, but there is a very strong presence and very strong desire and very strong fit for our printed tooling out there. And like I mentioned, it's really for people who need 5 to 100 shots of a part to be able to vet out their mold tooling and vet out their design process. Because we all know if we can afford, within our budget of time and money, if we can afford 5 prototypes instead of 1 prototype, we're going to end up with a better final design, and that's what we're all about here. So some of the benefits of using the PolyJet printed tooling as opposed to just printing the part directly is that we get to use the true material. So a lot of times printed parts take advantage of thin walls, or they take advantage of, say, a living hinge, like in the case of that purple part there. It's very difficult for us to print parts that operate exactly like, say, polypropylene or acetyl, especially in terms of, say, that living hinge there. Now we can print a part that looks exactly like it, and we can print a part that behaves with that living hinge aspect for a little while, but eventually the printed part's going to fail. And that's just the reality of it. Whereas an injection molded part would last a long time. So in this case, there's a very compelling reason to go through the extra process of injection molding the prototype, because it's going to give you a more accurate prototype in terms of functionality and also the process that would go through to be actually created. There's a time and cost savings. That's what we just talked about. We're seeing anywhere from 50% to up to 90% savings in time and cost. It's a very efficient process. We can print one mold and we can create 100 parts from that mold, and that they're fed into the actual injection mold machines. These aren't just done by gravity or done by hand. They're fully automated machines, just like you're using in a real production scenario. So it's a very efficient way to create these parts. And again, it comes down to early detection. If we can print a mold in a single day and we can get it on your machine the next day, there's not a lot of waiting around for parts to test them, to find out where the flaws are in both the part and the tool design. And also, we can find, in terms of early detection, again, because we're using the true to spec materials, we can, as opposed to, prototyping in a material that's doesn't quite have the performance of the true to spec material, we see material performance issues earlier on as well. So here's the success story. This is filmed by Stratasys, and this is a company called Seuffer, and they make plastic injection molded parts. I will have the sound on this, but it is not in English, so be prepared to read the subtitles here. But this is about 2 minutes long, and I think this can explain the benefits of injection molding probably better than I can. All right, so we're going to go ahead and play this.
Firma Seuffer ist kein Start-up-Unternehmen. Firma Seuffer gibt es urkundlich erwähnt schon seit 1766 und wir arbeiten in dem Bereich der Elektronikentwicklung für die Bereiche Fahrzeugtechnik, weiße Ware und Automotive. Kunststoffteile werden bei uns in der Größenordnung 12 bis 15 Millionen Stück im eigenen Hause gefertigt, eine ähnliche Menge von extern zugeliefert. Wir produzieren einen jährlichen Umsatz von ungefähr knapp 100 Millionen Euro Umsatz.
Wir hörten von einem 3D-Drucker, dass es sowas gibt, der schnell Teile aus Kunststoff herstellt. Und da haben wir auf einer Messe so eine Vorführung gesehen. Ich war begeistert und wir haben uns einen 3D-Drucker beschafft. Auf unser 30 Pro 3D-Drucker haben wir neben normalen Musterteilen auch versucht, Formen zu drucken aus Kunststoff, indem wir solche Hotmelt-Kunststoffe abspritzen. Das dient dazu, um Kabel zu dichten, um Leiterplatten einzuführen. Als weiterer Ansatz war, Formen zu machen für die Spritzgussmaschine. Das kann man auf einer Connex machen. Da erscheinen solche komplexe Sätze, Werkzeugsätze. Das ist das Gegenstück.
Durch den Einsatz von gedruckten Werkzeugen sind wir in der Lage, die Entwicklungszeiten von Werkzeugen erheblich zu reduzieren. Wir haben die Möglichkeit, erste Entwürfe schon nach wenigen Tagen zu begutachten. Wir haben darüber hinaus die Möglichkeit, die Entwicklung günstiger zu gestalten.
Für die Herstellung dieses Großserienwerkzeuges benötigen wir 8 Wochen Zeit und so ein Werkzeug kostet ca. 40.000 Euro. Diese gedruckten Werkzeugeinsätze liegen in der Preisklasse von 1.000 Euro und sind innerhalb von einem Tag herstellbar. Mit den gedruckten Werkzeugen kommen wir deutlich schneller zum Ziel und brauchen weniger Optimierungen an dem Serienwerkzeug.
Basically, what I wanted to get across here is that this is an application that I don't think a lot of people have thought about, because everybody thinks about using 3D printing for, printing the prototype directly. But, if you follow these 201 webinars where we go through specific applications, what we start to see is that there's a lot of tooling and manufacturing applications that we normally wouldn't think about. I used to work for a medical company myself, and we had injection mold capabilities on site. And my first task out of school was to create this part. It ended up having to be like a silicone part. Create this part for basically R&D. So I only needed 8 of these small silicone parts. And, just going along with the flow, going along with what I had been told been done in the past, I created a mold, a steel mold in SolidWorks, and I kind of went off the design of a past engineer, and I sent it out to the machine shop. And the machine shop came back and said, yeah, we can do this. It's going to be $10,000. And to me, fresh out of school, that was a huge number to me. And, so I kind of sheepishly went back to my manager and said, this is the number they came back with. And he wasn't surprised, but he said, you know what? There's some things that you can change in this. This is a little bit, this is not the best design. So I made these suggested changes that eliminated some of the processes that would have required like custom sized pins and EDM. And I went to the machine shop and they came back and they said, okay, well, we can do this for $6,000 now. And again, big number to me, but my boss was ecstatic with that. So we said, go ahead. And I think it took about 10 days. So the next week I had a mold. I took that to our mold guys, and they loaded up and they shot 8 silicone parts out of it. and at a cost of $6,000 for 8 parts. The sad part about this story is that we had a 3D printing machine, and this 3D printing machine had access to it. I just hadn't been told that I could use it in this way. So I could have saved the company a lot of money, and I could have looked like a rock star on basically my first week at the job, but I hadn't been told that the machines could be used this way. And so that's what I'm kind of hoping to get across here with these 201 webinars, is that we can use these machines in a lot of ways that isn't well known. All right. So if you have any questions about what you've seen, and if you want to ask them now, there is a questions box inside the GoToMeeting toolbar. If you'd like to ask them at a later time, shoot me an email. If you'd like a copy of the slides, I'm happy to give those to you as well. Thank you guys again for joining. Hopefully you guys got a little bit of info out of this. And again, if you're looking for something a little bit more basic, we have the 3D Printing 101 webinar on our YouTube page, and also a 201 webinar, and then some 201 application-specific webinars. All right. So again, if you have any more questions or if you'd like the slides, shoot me an email, and thank you for coming.